Section 3, review of synthesis of aldehydes and ketones. Now, this is where many students hit a brick wall when they're studying organic chemistry 2. They don't realize that they need to remember all of those reactions of alkenes and alkynes and perhaps alcohols in the first semester organic chemistry course. So that's why the textbook author realizes that, and we have this section here in the textbook all on just review. So let me talk about the 3 different reactions aldehydes can be prepared that we've learned about previously. Reaction number 1, oxidation of primary alcohols. Now here I'm going to slip in a review reaction as well. Let's say I have a alkene that looks like this and I want to make a primary alcohol. We do this through hydroboration, followed by basic hydrogen peroxide, and this makes a primary alcohol. Okay, this carbon right here that I'm dotting is called primary because it's bonded to only one other carbon atom. Now the way to take a primary alcohol to an aldehyde is to oxidize it with PCC. If I treat this with pyridinium chlorochromate, and that's why we abbreviate it PCC, this will form an aldehyde. Now when you draw the aldehyde, it's customary to draw the hydrogen that's bonded to that carbonyl carbon. Only PCC will work. If you treat this with Jones, this gives you a different product. Okay? I always write Jones. I don't write Na2Cr2O7 H2SO4 H2O, which is the sodium dichromate, sulfuric acid, water. I just write Jones. If you need to look up the letters and all that, you can do that. But this will give you a carboxylic acid, which is not, it's not the same thing. It's different. Okay, so only PCC will do that. Okay, so if you're making flashcards, which I do recommend, this would be a great reaction to put on a flashcard. Reaction number 2. Now this goes back to the first semester organic chemistry. Ozonolysis of alkenes. Alkenes, okay? So if we have an alkene, such as this guy here, okay, so this is symmetrical. And if we treat this with ozone and dimethyl sulfide, okay, this is what my students call a cleaver reaction. So think about the meat cleaver in the kitchen. This is going to cut or cleave this molecule into 2 pieces. And what you're going to form are 2 equivalents of, let's name this, propanol. Okay? The 3 carbons on the left end up as propanol, al, and the 3 carbons on the right end up as propanol. So you could put a 2 in front of this if you really worry about balancing the chemical equation. Now if they're unsymmetrical, you'll form 2 different aldehydes. Okay, so here we have a molecule with an isopropyl on the left, we have a methyl on the right, we have an alkene in the middle, and so you just need to be careful to count your carbons. Okay, that half of the alkene and the isopropyl group, when we treat this with ozone in step 1, follow dimethyl sulfide. Okay, so count your carbons very carefully when you do these reactions. You will form an aldehyde that looks like that. So you want to include this carbon atom in your aldehyde structure. Okay, now on the right, we have 2 carbons. Okay, we have the methyl group and then the single carbon of the alkene, and that's going to form a 2 carbon aldehyde. Okay, so that's acetaldehyde as we learned. Okay, and this, remember, we never use a numbering for the aldehydes. This is going to be 2-methyl propanol. Now lastly, I want to talk about cyclic alkenes. It is possible to have a cyclic alkene. Okay, so here I'm not putting interesting things on there. I'm just doing cyclopentene. And when I treat this with ozone and dimethyl sulfide, I'm going to form a total of 5 carbons. Okay? On carbon 1, that's this guy here, you're going to form an aldehyde. And on carbon 5, you're also going to form an aldehyde. Okay? So this is, I think it's called gluteryl dialdehyde. Don't worry about naming dialdehydes, okay? So this would form a dialdehyde. So that ring pops open and forms one molecule where you have the 2 aldehydes at the 2 termini of the parent chain, okay? So review that. This is section 9.11, okay? Section 11 in chapter 9. So go back and review that if you're a little stuck on that. The third way you can prepare aldehydes is from alkynes. And this comes from section 10.7, okay? 10.7. For reaction 1, in case you're taking notes and you need to know this and review it, that's chapter 13, section 10, okay? And these section numbers are from the 2nd edition textbooks. You might have to look around a little bit if you have the more recent editions. Now, alkynes, as you know, we're talking about terminal alkynes, have 2 carbons, okay? And the carbon on the right has a hydrogen. We don't draw it. But if we treat this with borane, there's special hydroborating reagents, but I'll just write BH3 for this. Hydrogen peroxide and sodium hydroxide, okay? These 2 carbons are going to be changed, okay? You form an aldehyde, okay, at the terminal carbon. So this is what we call the terminal carbon. Of the aldehyde, or a terminal alkyne, and this is now carbon 1 of my longest chain. Whenever you're doing these reactions, I do highly recommend that you number your carbons, because if you come up with a different number of carbons, you know you did something wrong. Okay? Carbons 1, 2, 3, 4, yeah. So that's good, okay? So we're forming 3-methyl butanal. Okay, and we don't have a number for the aldehyde. Okay, so there's not really a whole lot of interesting stuff there that we could be talking about for the terminal alkynes. This example is good enough in my book, okay? So once again, if you're making flashcards, this would be a great reaction to just stick on there, okay? Now let's talk about ketones. There are 4 different ways to make ketones that we've learned about so far in the course, okay? The first one is to oxidize secondary alcohols, and this comes from section 1310. Okay? If you have a secondary alcohol, like so, really doesn't matter what else is on there, okay? And what we want to use is the Jones reagent, okay? You can look up the specific reagents. It's sodium dichromate, sulfuric acid, H2O, but oftentimes just writing Jones is good enough. That's a Jones oxidation. This will change that secondary ketone alcohol into a ketone. And if you're careful and controlled, perhaps you can maintain that stereochemistry there at the carbon 2, okay? So I won't try to name this. It involves stereochemistry, but it should be fairly simple for the student to do that. So any kind of secondary alcohol. Okay. Doesn't matter if that's the R or the S alcohol, does it? And I treat this with Jones, the Jones reagent. Okay. I'll make what is that? I'll make the ketone. That's 3-heptanone. Okay, so it doesn't matter if it's cyclic or acyclic. You could even have 2 alcohols in there. Let's do one of those. Okay, so if I treat this with Jones, I'll make a dione, okay, or a diketone. Of course, it's in excess for this reaction to occur. Okay. Reaction number 2, ozonolysis of alkenes. We just talked about that. When you ozonolyze an alkene, you form aldehydes. And now I'm saying when you ozonolyze an alkene, you form ketones. So which is it? Let me show you. You form both. It depends on the structure of your alkene. Okay? So if you have something like this, okay, and you treat this with ozone, again, it's a cleaver reaction. It cleaves the molecule. Okay, so step 1 is ozone. Step 2 is dimethyl sulfide. And this can be read up in section 11 of chapter 9. And what you'll form are 2 equivalents of acetone. Okay, you can balance it if you're worried about that. Once again, if you have an unsymmetrical molecule, I'll make this side be a ring just to be creative. So we've got a 6-membered ring there, a cyclohexane kind of doubly bonded to this alkyl kind of chain there. Okay, so when we treat this with ozone and dimethyl sulfide, it might be a good idea to count your carbons. So we got 1, 2, 3, 4. So we're going to form a ketone that has 4 carbons. Okay? And that's from this piece on the left. Do not forget to include that carbon of the alkene in your ketone structure that you're trying to draw. Now on the right, I'll use green maybe to emphasize the different colors here. You're going to involve this carbon atom of your alkene in the structure of the ketone you want to draw. So this is just going to be cyclohexanone, okay, cyclohexanone. So you're going to form 2 different molecules if you have an unsymmetrical alkene. Okay? And here I would like to emphasize the complexity of the situation. If you have a molecule that looks like this, okay, and you treat this with ozone and dimethyl sulfide, again, this is a cleaver reaction. On the left, you're going to form 1 equivalent of a ketone, okay, and on the right, you're going to form 1 equivalent of an aldehyde because there's a hydrogen here, okay, there's a hydrogen there. So that's going to be pentanal, okay, you're going to form pentanal from that fragment. I'll draw it in the same exact orientation so you kind of see the arrangement of the carbons and how and where they end up. Okay, so that's pentanal. All right, so you can form ketones, you can form aldehydes, you can form both. They could be cyclic, it could be very complicated, okay? Number 3, hydration of alkynes. So again, we're talking about terminal alkynes, and we'll just show one example for this. Okay, and the way to hydrate an alkyne is pretty much water and acid, but you've got to use mercury ion in there. Okay, there's sulfuric acid, there's water. Okay, so water is the reactant, mercury ion, H plus, or the catalyst. I should have reversed those on the arrow. And what you form here is a ketone. Okay, and the carbonyl. Again, the carbonyls are carbon-oxygen pi bonds. Okay, you're going to hear that term a lot. The carbonyl is created at carbon 2. Okay, at carbon 2. So the internal portion, okay? This can be contrasted with the hydroboration. If you treat this with borane, basic hydrogen peroxide, you're going to form this molecule here. Okay, same number of carbons, just the carbonyl is going to be introduced at carbon 1. So pay attention to the regiochemistry to help you predict which one you form. We use something called Markovnikov's rule. Okay, the hydration of alkynes is reviewed in section 10.7. Okay, this reaction in a light blue would be great for a note card if you're studying and trying to remember these and review these very well for future more complicated synthesis. The final way we've learned about to create ketones is through the Friedel-Crafts acylation. And we've learned, for example, that aromatic rings of all sorts with deactivating groups and activating groups can react with acid chlorides, aluminum chloride, to form ketones, aromatic ketones, okay, aromatic ketones. So this is not acetophenone, it's slightly different. So we won't try to name this here, but that's just an example of that, okay? So don't forget, that's a ketone, that's a ketone. And it comes magically just from like an aromatic ring. So if you go from an aromatic ring to a ketone, like where did that come from? Think and remember the Friedel-Crafts acylation, okay? Now that we've been through all of this, let's do the problem 5 here that they propose in the textbook. It says identify the reagents necessary to achieve each of the following transformations, okay? So to go from a secondary alcohol to a ketone, we can use the Jones oxidation. To go from a primary alcohol to an aldehyde, we can use PCC, or pyridinium chlorochromate. To go from a terminal alkyne to a ketone, this is where we need to do the acid catalyzed hydration. So water, acid, okay, and some mercury catalyst, okay, mercury ion catalyst. How do we go from an alkyne to an aldehyde? Oh, that's where we need to do the hydroboration. So it's a 2-step deal, borane, followed by basic hydrogen peroxide. So hydrogen peroxide is H2O2, and sodium hydroxide is a base. How do we go from this alkene to this opened up thing? That's the ozonolysis. And here's a great example. I didn't think of showing you this one, but here you form a ketone on the left, and here you form an aldehyde on the right, okay? So if you're stuck with just memorizing, oh, alkenes can go to aldehydes and alkenes can go to ketones, you might be stuck with this problem. But realize it's possible to do both. And we do that with ozone, followed by dimethyl sulfide. And the last question, we're going from an aromatic ring to like a ketone. That's going to be your Friedel-Crafts reaction. Make sure you sketch in this whole structure with this methyl group going down, the methyl group to the right, with the exact same branching. Okay, don't modify it at all. Keep it exactly like that. Just put a chlorine instead of the aromatic ring, put a chlorine. Now down below the arrow, don't forget, you need the activator. It's aluminum chloride or aluminum trichloride, okay? So that's it for review. I do hope you work through flashcards and you review those sections as you need if you're a little stuck on things. Thanks for watching.